Okay, welcome back to the elementary psychometric studio here. And today's topic is going to be a rather specialized one, having to do with the relationship between test length and reliability, specifically how to estimate the impact of changing the length of a given test or scale on its reliability. Again, now this is something that you may or may not find necessary on a regular basis, but it can come in handy because there are multiple situations in which, in fact, we have reason to want a test's length to change. So without further ado, we leap into slide share mode, and here we go. Now, one thing you should remember is that if you want to increase the reliability of any sort of measurement instrument, there are really only two ways to do it. One of them is to simply take more measurements. If I'm wearing a little doohickey that's supposed to estimate how many miles I've walked, and I have my doubts about how precise the thing is, I can take the same walk numerous times and average out the results and get closer to the true length of my walk. If I'm administering a midterm exam that has a certain number of items on it, and I'm concerned that it's not giving me a precise enough estimate of my students' learning, I can actually add more items. And instead of giving them a 40-item test, I could give them a 50 or 60-item test. That's one way. The only other way is simply to take better measurements, buy a better little doohickey to keep track of your mileage, to learn how to write better midterm questions and so forth. The latter, of course, is something we can't always do. We don't always have available the ability to improve on an item by item level, a measure by measure level, what we're doing. In any case, today, we're really only concerned with the first option. So always remember, if everything else is held constant, that's an if, then adding items to a test or personality scale or what have you will make it more reliable. And of course, deleting or subtracting items will make it less so, will reduce its level of precision or reliability. Now we're going to get into how you predict what's going to happen. So you can have a couple of scenarios here. One is where you have some kind of measurement tool, you have a scale that does what you want it to do, except it doesn't do it very well. It's not reliable enough for your present purposes. So as one of our running examples, I'm going to say that we are starting with a hypothetical 10-item narcissism inventory, which has a reliability of 0.64. Presumably that would be coefficient alpha, some internal consistency estimate. And perhaps the problem is that I want to start using this test, which up to now has been used only in research contexts, in clinical settings. And I feel that reliability of 0.64 just isn't good enough for clinical usage. So I need to make it longer. I need to add items to enhance its reliability, but how many? That sort of question. The other problem, the converse problem really, is when you have a relatively reliable scale, one that is precise enough, you have no problems there, but it's now too long for what you want to do with it. So the hypothetical example I'll use here is, what if you had a 30-item quality of life inventory with excellent reliability, 0.88, and you've been using this in some studies, using moderate-sized samples, maybe of undergraduates, you can catch in the classroom. And now you're wanting to move on to larger scale studies, maybe internet-based samples, maybe pooling your results with those for a number of other measures. And you're hoping to, get 1,000 people to do it. And your collaborators are telling you, look, you can't have 30 questions just for this one thing. We don't have room for that in the protocol. So if I want to participate in this bigger study, I've got to make it shorter. But how much shorter can I make it and still have a measure that is adequate even for research purposes? That arises less frequently, perhaps, than the problem of insufficient reliability, but it does arise. All right, so there are the problems. Now, as it happens, there are actually two different questions we can ask here. They're subtly different, but they're different. So one approach to the problem is to kind of predetermine an amount of change and ask, what would happen if I did that? So, what would happen if I wrote 15 more narcissism items? Or what would happen if I deleted 15 of my quality of life items? By what would happen, I mean, how much would reliability change? Where would I probably land at that point? We know it's going to go up in the first case and down in the second case, but by how much? The second possible approach, which in some ways is a better one, in my opinion, is to ask how much change is needed in order to get where I want to be, in order to achieve the level of reliability that I'm desire or I'm willing to accept. So suppose I want my narcissism scale to have reliability of at least 0.8, and I consider that to be a threshold perhaps for clinical usage. Or what if I want my quality of life scales reliability not to drop below 0.7? Maybe I'll consider that to be a threshold for the kind of research I want to do. Now, it actually is the same equation flipped around algebraically, but of course it's going to look different because it's been flipped around. So we'll look at each in turn. But very important, I'll probably circle back to this later on, we are assuming here that all the items are roughly equivalent in quality. Now, in practice, that's never 100% true. But for our present purposes, what's important is to understand that the procedures we're following are yielding approximations of what's going to happen. Also, that if I'm writing new items to make the test longer, the new items can't be garbage. They have to be about as good as the ones we had to begin with. And that can get hard after a while, by the way, without virtually repeating questions, which is just annoying. And likewise, items that we're deleting, we're basically selecting randomly. So on average, they're going to be average items. Now, there is a way of improving on that. We'll get to at the very end. It requires a little extra data collection and analysis, but you can do better than that. Okay, so first question, and this is our version 1 approach. What would happen if I increase the test length by yay much? So this is the formula. You can stare at it as long as you like, circle back to this. That essentially the reliability of the modified test, and we're using R sub mm for that, is equal to the factor by which we're going to change its length, come back to that, that's m, times its existing reliability divided by 1 plus, and then you got the parentheses, m minus 1 times the existing reliability. So we're going to work our way through this as we move forward. But what about m? The thing to remember about m is that it is a multiplier. In a sense, it's good that I think they used the word m because of modified, but the fact that it's a multiplier and that starts with m kind of helps us to remember this. So if the test is getting longer, m will always be a number greater than 1. If the test is getting shorter, it'll be less than 1. But it's crucial to remember that it is a multiplier. Now getting it is actually quite easy. You just take the length of the test that you want to have at the end and divide it by the length of the test as it is now. So if it's going to be a 20 item add-on to a 40 item scale, well, it's 20 plus 40. The new test will be 60 items long. The old one was 40. So m is 1.5. Again, oh, hello, cattail. Again, notice that it's always greater than 1 if we're making it longer. So getting it's pretty easy. New length divided by old length. That's all we really have to do. It's also very easy to louse this one up. Forgive me if you would never do this, but I've seen it happen too many times. When you get m, it's not the number of items you're going to add to or subtract from the test. It's the number you're going to multiply times the existing number of items. Multiply times the existing number of items to see how long the new test, the modified test, is going to be. Crucially important, although for some people perhaps painfully obvious. Okay, so here's an example working this out. We'll see the equation again, I promise. So we have our 10-item narcissism inventory with its sort of marginal reliability 0.64. And we figure, okay, look, I'm going to write 15 new items, and hopefully when I have a 25-item test, it's going to have high enough reliability to be useful. But how high? So before you sit down and write all those items, because the items, that's work, right? Before you write a whole bunch of items and find out you have too many or you don't have enough, let's figure out where we're going to end up. So here's our little equation again. And so what do we do? Well, the multiplier is 25, the new length, right? 10 plus 15, divided by 10, the existing length. So m is 2.5. We're making it 2.5 times as long as it was originally. No mystery there. The numerator of the equation is simply 2.5 times 0.64, 1.60. The denominator takes a little more arithmetic to work out, but 1 plus 2.5 minus 1 times 0.64 equals, et cetera, et cetera. It ends up being 1.96. And then you just divide, right? So the projected reliability of the modified test would be 1.6 over 1.96, about 0.82, a little under 0.82. So in fact, if we were aiming for 0.8 as a threshold value, we actually did a pretty good job of guesstimating where we were going to end up. But of course, if you'd been willing to settle for less, or if you wanted more, then you'd be kind of back to the drawing board and fixing it a bit more. So let's walk through one where you have a chance to begin setting it up for yourselves. So we have a proverb interpretation test with surprisingly low reliability, only 0.58, but it's only a 12-item scale. So we're thinking to ourselves, well, what if I just add 6 items, make it an 18-question test rather than a 12-item test? What will happen? So your first job, of course, is to solve for m. I'm talking a little more slowly and pausing more, hoping some of you are doing it. We can, of course, call up our calculator and do it over here on the side. So if I have 12 items plus 6, that's 18. I didn't need the calculator for that. Dividing that by the original 12 tells me that, okay, m is 1.5. So now you're setting up the equation. You have the existing reliability, which is 0.58. And for the numerator, you're simply multiplying that times the 1.5 we just obtained, and obtaining, surprise, surprise, 0.87. Going a little faster perhaps than I should for those of you working this out yourselves. But the denominator, which does take a little longer, right? So in the denominator, it's going to be 1 plus, and then you got the 1.5, 1 minus 1, and you've got all that stuff going on. If you remember your order of operations, you do the parentheses thing first. So 1.5 minus 0.5, I'm sorry, minus 1 rather, gives you 0.5. And then you multiply, so 0.5 times 0.58, and you should get 0.9. I guess I should do these by in front of you, times 0.58 equals 0.29. And then we're adding 1 to that. Probably didn't need the calculator, and I get 1.29. So my numerator, if you remember, was 0.87. I simply divide by 1.29, and I find, lo and behold, that I'm probably going to get the reliability up to about 0.67. 0.67, possibly 0.68. That's going to be the range, the midpoint of the range of likely outcomes. So I'll achieve some improvement, of course. Whether that's enough is up to your judgment. That's not something that the math answers. But there's that. Now, let's see. Now, the other way of solving this sort of problem will come in a minute, but first let's look at what happens if I'm decreasing test length. So, okay, and I won't walk through 2 examples of this, just the one. So we have our 30-item quality of life inventory, reliability of 0.88, and we want to essentially cut it in half. So, what are we going to end up with when we do that? If I could get away with 15 items worth of my QOL measure in this big study, is it going to be worth it? So same equation, no different there. In this case, M will be 15, the new length, divided by 30, the old length, or just 0.5. So the numerator, no biggie, 0.5 times 0.88 is 0.44. The denominator is just a wee bit tricky if you have trouble dealing with negative numbers. Again, I don't want to insult your mathematical background, but I found that some people stumble over negative numbers, because when you take 0.5 and subtract 1, you get a negative 0.5. And then when you multiply that times the 0.88, you get a negative 0.44. And as you should recall, when you add a negative number to something, it's actually the same as subtracting. So 1 plus negative 0.44 is the same as saying 1 minus 0.44, which means we end up with 0.56. So the projected reliability will be 0.44 over 0.56, or just under 0.79. So incidentally, in this case, I'd be pretty happy with that outcome. I'm losing some reliability for sure, but I've still got a fairly robust test to be moving forward with. Now, the other way of asking the question, or the other approach to these problems, is to specify what our goal is rather than what we're going to do. So instead of saying, if I do this, what'll happen, you're asking, what do I need to do to get there? Again, I kind of think that's preferable, but both approaches are legit. So here you have this variation on the equation, but in this case, we are solving for M. We know what the reliability we want is going to be, RMM. Of course, we know the existing reliability. We want to know what we need to do to get from here to there. Anyone who has any liking for this stuff, you look at that, it's kind of an elegant equation, isn't it? It's nicely balanced. So here we go. We're going to try to increase the reliability of our narcissism inventory from 0.64 to 0.8. And so here's our equation. And we just plug everything in. The numerator, 0.80 is what we're after, times 1 minus 0.64 gives us 0.288. The denominator, you take what we have, 0.64, multiply that times 1 minus 0.8, you get 0.128. You divide, and you have 2.25. Now that means that 2.25 is the factor by which we're going to change the length of the test. I said that slowly because it's important. The new test must be 2.25 times the length of the original. So always remember, it's not like, oh, I'm going to add 2 or 3 items here. It's, I'm going to make the new test 2.25 times the length of what it was. So that means we had a 10-item test. So to get to 0.8, it's going to have to be 2.25 so it's going to be between 22 and 23 items long to get where I want to go. Let's say 23 to be on the safe side. There's no such thing as half an item, obviously. We have 10 items, so I don't need to write 23 items. I need to write 13, right? 23 minus 10. So I now know that if I want to get to this 0.8 threshold that I'm considering to be important for whatever reason, I need 13 new items. So practicing on this one, again, we have our Proverbs test, 0.58, and I want to get it up to 0.8. I want to have a clinically useful measure of abstract thinking as indicated by proverb interpretation. So what do you get? Again, we'll call up our calculator and clear out what we had. So we know that in the numerator, we're going to have 0.8 times 1 minus 0.58. So let's see, 1 minus 0.58 would be 0.42, surprise, surprise, and we'll multiply that times 0.8, and the numerator will be 0.336. You have to remember that one now, or have it written down. And now the denominator, we actually do basically the flips of that, right? The reverse of that. So we're going to take 1 minus 0.8, 0.2, and multiply that times 0.58 to get 0.116. And so now I can solve for m. M is going to be 0.336, our numerator, divided by 0.116, our denominator, or about 2.9. I mean, that's so close to 2.9. Let's just go ahead and round it. So I had 12 items. So that means that I need to have a test that is about 35 items long, the 2.896 whatever times 12 gave me 34.758. Again, no such thing as a fraction of an item, so I probably need a 35 item test. And since I already have 12, the implication is I'm going to have to write 23 proverb items here. That could get hard, by the way. I don't know if there are 35. Well, there have to be more than 35 proverbs in our language, but that's a lot to try to scare up. But that's what you're going to have to do if you want to jack up the reliability on this thing by making it longer. Now, decreasing, same thing. We had our 30-item QOL measure, and we're willing to drop down to 0.7, just thinking of that as reasonable. So we set it up accordingly, solve for the numerator, solve for the denominator, solve for m. And we get a number pretty close to 0.32. It's 0.318 as it happens. So multiplying that times 30, we find that, yeah, we could probably get away with a test about 10 items long, 9.54, again, rounded up to 10. Always play the safe direction with this. And so we could actually eliminate up to 20 items if randomly and just use the remaining 10. There we go. All right. Now, I do want to emphasize, when you're developing a short form of a scale, there's a better way of doing it. Randomly eliminating items is okay if all you have is the list of items and no ability to collect any further data. But you can actually come out ahead if you collect a little more data here. Because remember, not all test items are performing equally well. So what we will typically do is, in a statistics program such as SPSS or the free JASP software, run what are called corrected item total correlations. And that's how strongly each individual item correlates with the sum of all the others. So if I have a 10-item test, how well does item 1 score correlate with the score for items 2 through 10 inclusive? How well does item 2's score correlate with item 1 and 3 through 10 inclusive, and so on? So what you're getting there is a measure of how strongly each item is contributing to whatever is shared, which is to say the reliability. Now, I did a quick example of this off screen. I didn't think you needed to walk through all the procedures in it, but I used normative data from a test of crystallized intelligence. You had hundreds of children tested here, and the original test was 32 items long and had really, very fine internal consistency. The reliability coefficient alpha was 0.906. Now, if I eliminated half the items, 16 of them randomly, I would end up with a predicted reliability of about 0.83, just shy of 0.83. Still not bad, but a distinct drop nonetheless. But when I ran the item total correlations and flagged the 16 weakest items, none of them were terrible, by the way, except a few that had very little variability. But I eliminated just those 16 weak items, and the reliability only dropped to 0.897. So if you're rounding, you're going from 0.91 to 0.90. which is not much of a loss. And you'll find if you look through the literature on personality tests and IQ tests and achievement tests and all that, that there actually are quite a few people who kind of do this. I don't want to say for a living, but maybe for tenure. It's one of their pet projects is find a pretty interesting scale that looks kind of on the long side for many folks to use it, and collect a little data, run these analyses, shorten the thing down, and lo and behold, you've hardly lost any ground. You often, by the way, do lose something when you do that. You may find yourself losing some of the breadth of coverage of the construct, but that's a validity issue, not a reliability issue. So moving ahead, again, that's getting a little more advanced there, but moving ahead and towards our conclusion, we can say that there are times we have scales that just aren't reliable enough for what we want to use them for. And one way of doing that is to add items, to improve them rather, is to add items. But of course, that takes work. And we also don't want to make the thing so long that no one wants to take it. So we want to add sort of the minimum number of items that are necessary in order to achieve our goals. These formulas are helpful in making decisions about how much we're going to add to what we have, how much work we're going to invest, and how many questions we're going to make our research participants or our patients answer. On other occasions, less frequently, but it happens, we have a scale that's just too long, and we're willing to make a shorter version, but we want to know how much, damage we're going to do to it in the process. Here, again, we can use these formulas to estimate how much we're going to lose. But again, I want to emphasize that in the actually not uncommon situation where you're trying to shorten a test, you really want preferably to eliminate just the weakest items, to be more selective. And often when you do this, as we saw in the example just now, you can do it with minimal effect on the overall reliability of the scale, sometimes to a remarkable degree. But to do this, though, you have to collect, a fresh set of test protocols and conduct a proper item analysis, and then you're done. And at that point, as we say, we're done too. So good day to you, and we'll see you perhaps for another in the series.